So today we're going to focus on generalizing our Newton's law to a situation that is more of a proper 3D situation than we've had so far. So far we put everything in between two parallel plates. We oriented them with with our coordinate system, and we had only one velocity that was non-zero, which was in x direction, right? And the others we assumed are zero, so we just simply didn't look at them. And we looked at the transfer across or along one other direction, which is y direction. So we had basically xy situation, and that was it, right? So it was a very simplistic situation. In general, our fluid flow is described by velocity vector at every point. So at every point, I have a vector that can point in any possible direction, right? So it has 3 dimensions. So in that sense, I have a vector field that maps, so at every point, I have a velocity. Okay? So a point is described with 3 values, x, y, z, and velocity is described with 3 values, vx, vy, vz. And that's assuming a steady state situation where things are not changing in time. In reality, I also have a change in time. So with every x, y, z, and t, I'm associating vx, vy, vz that is function of all of these 4 things, x, y, z. Right? So it's a lot to keep in your brain, right? So I'm going to start with visualization, and I also want to point out an excellent resource for review. So these are Khan Academy that you might or might not have heard about. It's a free set of modules, teaching modules online. And they run from anything in elementary school up to college. And it's pretty good coverage of standard college topics, multivariate calculus included. In specific, and I actually finally found the name, there's this person, I'm going to show one of these videos, but there's this... His name is Grant Sanderson, and he also on YouTube goes by 3 Blue, 1 Brown. So he has a YouTube channel. I don't know that he's working with Khan Academy anymore, but he does have his YouTube channel. And in anything in terms of both mathematics, so vector fields, so multivariate calculus, to all of the physical applications. I was recently reviewing magnetism. Has excellent videos and excellent visualization. So the software that he uses for visualization is his own, and it's one of those out there things that is really good. Okay? So if you need an Khan Academy system of videos, is following the general rule that all of the videos should be around 10 minutes, but not exceeding 20 minutes in length, which is correlated with human attention span. Okay? So human attention span really is 7 to 10 minutes, research says, and then after that you kind of fade, and maybe you bring yourself back, maybe you don't. Okay? So essentially, there's a value in having 10-minute short slides. So in that sense, you can watch it on your phone. You can even daily, if you set yourself up for a review of these topics day by day, 10 minutes per day can actually go a long way just to get you started. We're gonna, by the end of this class, we're gonna come up with Navier-Stokes equations, which are these vector equations, okay, that look extremely cryptic, okay, because they make use of vector operations. They're efficient to write down mathematically, but hard to visualize. And watching these videos will kind of bring that visualization back into your mind when you're thinking about it. One thing that you have to keep in mind, absolutely, as hairy as this math can get, that math took 150 plus years to work out. And it was developed in function of physics, not the other way around. So all of these operators are not here because mathematicians thought that they would make students' life painful. Okay? They're actually simply efficient, difficult, but efficient tools to deal with vector fields. So when I spring divergence and gradient and curl on you, okay, and you look up these formulas, you will ultimately just look up in the back of the book and quickly calculate them. And yes, you can just focus on the formula and efficient calculation of a divergence. But divergence is a specific quantity that has a specific physical meaning that I want you to think about. Okay? And it was brought into life because of that physical meaning, not because somebody thought it would be cute to compute. Okay? Yes, math on its own went into development and further generalized it and made like an entire theory behind it. So yes, math does run away with things like that and generalizes them further into something that is not always comprehensible. But it came to being because of physics. So every time you kind of get frustrated with it, just do remember that it's actually a beautiful tool in function of physics. So I'm just going to actually play this video that you see an example of this video. And this is just a very simple, it's relationship of fluid flow and vector fields. A lot of vector fields and mathematics is actually exemplified through fluid flow. So what a beautiful way to start, and it's a 3 minutes well spent. Sound is really... Where's the sound here?
How would you describe this flow mathematically? So, as you can tell, the particles are moving in some different way. Over here, they're kind of moving to the left. Here, they're moving kind of quickly up. Over here, they're moving more slowly down. So, what you might want to do is assign a vector to every single point in space. And it's not an attribute of the way the fluids flow. This isn't necessarily obvious, but if you look at a given point,
just a moment. I need to up the volume on this system. Let's try now.
In space. Well, let's say like right here. Every time that a particle passes through it, it's with roughly the same velocity. So you might think over time that velocity would change, and sometimes it does. A lot of times there's some fluid flow where it depends on time. But for many cases, you can just say, at this point in space, whatever particle is going through it, it'll have this velocity vector. So over here, they might be pretty like high upwards, whereas here, it's kind of a smaller vector downwards. Even though, and play the animation a little bit more here. And if you imagine doing this at all of the different points in space and assigning a vector to describe the motion of each fluid particle at each different point, what you end up getting is a vector field. So this here is a little bit of a cleaner drawing than what I have. And as I mentioned in the last video, it's common for these vectors not to be drawn to scale, but to all have the same length just to get a sense of direction. And here you can see each particle is flowing roughly along that vector. So whatever one it's closest to, it's moving in that direction. And this is not just a really good way of understanding fluid flow, but it goes the other way around. It's a really good way of understanding vector fields themselves. So sometimes you might just be given some new vector field, and to get a feel for what it's all about, how to interpret it, what special properties it might have, it's actually helpful, even if it's not meant to represent a fluid, to imagine that it does, and think of all the particles, and think of how they would move along it. For example, this particular one, as you play the animation, as you let the particles move along the vectors, there's no change in the density. At no point do a bunch of particles go inward or a bunch of particles go outward. It stays kind of constant. And that turns out to have a certain mathematical significance down the road. And you'll see this later on as we study a certain concept called divergence. And over here, you see this vector field, and you might want to understand what it's all about. And it's kind of helpful to think of a fluid that pushes outward from everywhere. And it's kind of decreasing in density around the center. That also has a certain mathematical significance. And it might also lead you to ask certain other questions. Like if you look at the fluid flow that we started with in this video, you might ask a couple questions about it, like it seems to be rotating around some points, in this case counterclockwise, but it's rotating clockwise around others still. Does that have any kind of mathematical significance? Does the fact that there seem to be the same number of particles roughly in this area, but they're slowly spilling out there. What does that imply for the function that represents this whole vector field? And you'll see a lot of this later on, especially when I talk about divergence and curl. But here I just wanted to give a little warm-up to that as we're just visualizing multivariable functions.
Okay. So again, vector fields can represent a lot of things. It could be a force field. Force also has a direction, so at every point I might have force field, or I might have velocity field, and so forth. And these mathematical tools like divergence and curl that we're going to introduce as we go along still simply tell me something, give me a number that tells me something physically about either flow or flux, so the force field, whatever this physical significance might be at that given point. And that can be very useful. So again, don't get frustrated with a lot of cryptic signals, symbols as we go along. So without further ado, let's start generalizing. So this is just to tell you where we basically are still going through the chapter 1. We studied molecular basis for viscosity, so we call that kind of done and over with. We have a better understanding of how viscosity or the friction, internal friction that we kind of feel relates to the fluid motion. So now we're going to actually look at the three-dimensional version of the simple Newton's law that we have considered so far. So I'm going back to chapter 1.2, and then we're going to also go through chapter 1.7. Okay. So Newton's law of viscosity is, okay, I'm back to this situation of not showing. No? It didn't swap the displays. Okay, I'm going to leave it as is, but it's a little annoying. Newton's law of viscosity is tau yx is minus mu dvx dy. And as I said, we actually looked at a very simplistic situation when we described this. Okay? Nevertheless, we did assign it directionality. Okay? So we were looking at the change or the difference in Vx velocity, x momenta, okay? I have a difference in x momentum or x velocities. I'm assuming a constant density here, rho, so whether I multiply with it or not, it doesn't really matter. Okay? So my momentum is simply rho Vx. Okay? So when I have differences in velocities, those differences in the layers of fluid will basically cause momentum transfer in y direction. So the direction itself is orthogonal to the velocities. And that's basically, I have x and y directions here that are orthogonal to each other. Now, that doesn't mean that I don't have transfer in all other directions. This is just because I just looked at one velocity that is non-zero. And this velocity, Vx, was a function of y only. Okay? Because all of in this particular case, along x direction, my velocities were the same. So there was no need to differentiate them. My velocity was really just a function of y here. So in that sense, this was an extremely simplistic situation. So, and nevertheless, I can still imagine sort of a box of fluid, okay? And there is this y plane, okay, that is orthogonal to y direction. And my momentum transfer is going across that direction. Now, the only thing I had to transfer was my x momentum in this initial case. But in reality, I might have both x momentum, y momentum, and z momentum, all of which could transfer across this plane. So in a general case, I actually have a velocity field. That velocity field has x, y, z. Okay? And I can transfer, as long as I have differences in those vx's, vy's, and vz's, I can transfer them across this y plane. Now, to fully describe the situation, of course, I don't just stop at y plane, I do the same thing across x plane and z plane as well. And suddenly there's 3 things I can transfer across 3 possible planes. So I have a 3 by 3 tensor components that I need. And this situation of this transfer, that's why I actually need a matrix to describe it, which is going to be our stress tensor. Okay, so tensor is simply described by a matrix. Tensor ultimately acts on a vector, and in this case, I can assume it acts on a vector sort of in this particular case, I'm looking plane by plane. Okay? So my vector of action is actually this y direction vector, or z direction vector, or x direction vector. But in general case, I have a general vector, so I'm going to multiply that vector with my tensor and get another vector as a result. So that's what tensor fields mathematically do. Yes?
I just wanted to ask something about the word in matrix and tensor. I mean,
matrix is a mathematical description of a tensor.
Okay.
However, in a different coordinate system, I'm going to have a different matrix representation that doesn't change my tensor physically. It just really changes its representation.
Okay.
So my actual numbers depend on the coordinate system I'm using. But mathematically also, I can transfer, like I can easily convert from one coordinate system to another coordinate system. Well, easily, yes. I mean, I have a matrix that does that.
And then something like a vector, which is just a 1 by 3, like a 3 by 1 matrix, you just call that a tensor as well? Or
no, vector I call a vector typically.
And usually stress x-axis is always 0. I mean, like momentum in parallel to the motion direction. Is it 0, or do we have a tau xx or tau yy?
We do have tau x's because yes, I can transfer along that direction too.
So it's possible to transfer
Yes.
momentum along the velocity.
So as long as I have differences in velocities, yes, I can transfer along that direction. Now, we're going to get to that. Oh, I'm going to get ahead of myself. So this is tau yx, describes solely what happens when I have differences in velocity. Okay? I could have some tensor that acts in the absence of the, so basically just things sitting still. Okay? And that I describe by thermodynamic pressure. And that's something that always acts orthogonal to the surface, never parallel to it. Okay? So we're going to separate the two. All right. So if I generalize, so this is my coordinate system, x, y, z. I am describing my little coordinate vector as delta y. I'm following the book in that sense. They use delta x, delta y, delta z. I personally like ex, ey, ez, but I wasn't consulted in the 1960s when they wrote the book. Yeah. I wasn't born in 1960 when they wrote the book. So in any way, we're using delta x, delta y, delta z as coordinate vector description. It's just the notation. So this vector describes my coordinate plane. And we typically take a little box that has sort of dimensions that we will shrink as we get to the differential equation description of things. But right now, I'm just visualizing a little box of fluid. Okay, so I have a vector, and this is just general vector B that has values in x, y, and z directions. Okay? And I can again look at the transfer, okay, of my x, y, and z momentum across this y plane. So since I have 3 things here to transfer, I'm going to have a vector that describes this. Okay? And that vector I'm going to call tau y. So this is tau yx is transfer of x momentum across y plane. Tau yy is transfer of y momentum. I still have y momentum. Yes, I can transfer it across y plane. And I have z momentum that I can transfer across y plane as well. Okay. Now, how do I orient this, like who is first here, y or x, is a matter of agreement. Here we agree that we say, okay, tau yx is transfer of x momentum across y plane. So first comes the plane, then comes the velocity direction, or force direction for that matter, if I'm looking at the forces. That's a matter of agreement. Good news is that in the end, it really won't matter because it's a symmetric tensor, so components will be similar. So whether you make that mistake or not, it doesn't matter in calculation, okay? But do know that it's a matter of agreement, and in a different field, it might be a slightly different agreement, okay? So then similarly, I could look at the x, y, and z momentum and transfer it across x plane, okay? This x plane is orthogonal to x coordinate, right? So I need a piece of paper. This piece of paper will do. So I had a y in this, I had a y, okay? I could have x and z. So if I transfer the same momentum components across z, I'm gonna have 3 more values, have z. So basically, this is my generalization, so I put all these numbers into a 3x3 matrix, and I'm calling it a tensor. Now, that's the viscous force, that basically it's a viscous force per unit area. And we're looking at either as a transfer of momentum or also a force. So force would be, right, the viscous force that my bottom portion of the fluid was exerting on the top portion of the fluid. If I had that same thing worked out in x direction, then I would go to the lesser x values and the force that they exert on upper x values. So in that sense, I'm orienting things in a coordinate system. So I can either look at the momentum or force view, either way. So this force itself, though, does it have the same direction as the momentum transfer? Let's go back to our favorite y-plane. When I looked at the tau yx, my force was a shear force. The force itself was in this direction, right? But momentum transfer happened this way. So conceptually, that's something to keep in mind. And do I have any viscous force if I don't have the difference in velocity? So if both of these boxes, if both of these boxes travel together, there's no relative difference in velocities, then I'm not going to have this friction here that I found, right? So in
it's
that,
a solid.
Huh?
In that case, it's a solid.
Yes, but that's what I had.
No,
Thanks
but
for
if you
pointing
look
that out. But yes, it's also, and in that case it behaves as a solid. Yes, I'm aware of working solids, but yes, his point is that I will just have, it's basically, as I'm moving, it's translation of a solid in that case. So in that sense, in that case, it's the same. So, however, we do have some forces that are acting in the absence of the differences here in velocity. And those are my thermodynamic pressure forces that I mentioned already. So we need to look at them separately. And we know that pressure has a habit of working orthogonally to the surface, right? Whatever surface, and however that surface might be oriented. So if I'm actually looking at a tensor that describes that, I'm still going to use the same approach. So the way to parse that, to actually get this tensor, or the way to write it down, okay, is that we look at the components that go across different planes. Okay? So I can do the same with the pressure. Okay? So if I'm looking at a yx component of the pressure, I'm going to have nothing because nothing is shearing, right? The only thing that gets transferred is the one in that direction, right? So if I'm thinking of a tensor that describes that, I'm going to have something on diagonals in places x, x, y, y, z, z, and zeros otherwise. Okay? And that's simply, and then when I look at that as a tensor, even if I look at some generically oriented surface in that particular coordinate system, I'm still gonna get that action by multiplying my entire tensor, which is a diagonal thing, onto the vector that is normal to that surface, and I'm gonna get what I need to get that way. Because that's how we break things down in coordinate systems and the way that things act in coordinate systems. So that simplistic tensor will still work out on a generally oriented surface if I need it to. So I do have to add those, and again, I'm going ahead of my slides. So direction of the hydrostatic force is always normal to the exposed surface. So I'm going to describe that action, okay, as P times delta y if I only have y plane, P times delta x, and P times delta z. And P, since I'm assuming isotropic situation, there's no reason for me to think that thermodynamic pressure would work differently in different directions. Or until there is a reason to think that, I'm not going to assume that there is. So when I actually put the total, what we're going to refer to as molecular stress tensor, okay, I'm going to have in these directions x, x, y, y, z, z, I'm going to have both the shear stress component and the thermodynamic pressure. And in the shear directions, I'm not going to have any pressure. Yes? So basically, it's P times identity matrix plus my tensor, shear stress tensor. Okay? So this is now a tensor which I'm going to call molecular stress tensor P. Okay? And this is the cryptic part. Okay? I don't want to constantly write matrices and 3x3 things. Okay? I want to condense what I'm writing, so I'm actually going to refer to entire tensor. This is my delta, this is my identity matrix. I like using I, but again, I was not consulted in 1960. And there's the shear stress tau, and this is, sometimes we're gonna just do these two underlines. This is mechanics habit, or solid mechanics habit, in fluid dynamics that has been influenced by mathematicians, they don't like that. So often we'll just say P, delta, and tau. But they are tensors. And pressure is a constant. Okay? So this is a tensor notation. Again, sometimes we will use it, sometimes we will not. If I look at the coordinate components, this basically what this means is that for every, out of all of the possible ij's, which are x, y, z, every individual component, bij, is p times, this is called Kronecker delta, delta ij. It's 1 if I is equal to j, so if I have x, x, y, y, and z, z. If you like those coordinate notations 1, 2, 3, then 1, 1, 2, 2, 3, 3 components will be 1, others will still will be 0. So that's simply a shorthand notation for this identity matrix here, plus tau ij, so again, coordinate by coordinate. Okay? So this is, it's called Kronecker delta, delta ij. Okay? So then Pij is my total molecular force in which direction? Per unit area perpendicular to which direction? This is easy to flip. So molecular force is in J direction per unit area perpendicular to I direction. Just remember tau yx is x momentum in y direction. Okay? Or force in x direction across y plane. So that kind of mentally write it down, tau yx, and quickly work out which one is which one. But in general, if I generalize this, then Pij in this matrix is the total molecular force. Again, by total molecular force, I'm adding viscous forces and thermodynamic pressure forces in J direction per unit area perpendicular to I direction. So this is my generalization for the molecular stress tensor. And again, my flux version of this is flux of, again, J momentum per unit area perpendicular to I direction. Okay, so this is my generalized tau. So now I'm wondering, okay, what do I do for, this is a very nice and general way. There is nothing I said about fluid so far, actually, just in the way I described this tensor. So this tensor view in our most general equation down the road is actually valid for regardless of the fluid. But in practice, I got to compute for a specific fluid. So now I'm going to specialize this for Newtonian fluids, and this actually Newton's law that is valid for Newtonian fluids. Right? So in most general case, if I was just generalizing altogether, I would have that my tau is combination, well, if I didn't know any better, of all of the possible partial derivatives. Okay? So I would have 9 of them and 9 coefficients. And I would have these 9 coefficients for every version or every component of the tensor. So 9 by 9 is 81. That's too many. Okay? Now, in general, you do have a potentially 81 different components. But then you simplify, okay? And you can actually go, we're not going to go through the details, this is in fluid dynamics books, but just to give you some idea. In the state of pure rotation, you know that that's basically the solid case that we just mentioned, there should be no viscous force. And you can actually see problem 1D1 in your textbook if you were interested. So you will actually, and more generally, you also have to conserve angular momentum, which we're not going to talk too much about in this portion of the course. And you're going to actually see that, or you can find that that leads to the symmetricity. So tau ij has to be equal to tau ji. So that's kind of powerful, because that simplifies if my tau yx and xy have to be the same, then I actually can look at these coefficients and simplify them. I don't have 81 anymore, right? Obviously. So basically, because of my viscous stress is symmetric, I can also see that my coefficients A, E, I, they have to essentially be 0 unless I have this symmetric part of the tensor, x, x, y, y, z, z. So that's one simplification. And then also my fluid is isotropic, so there's no reason for me to think that there is a preferred direction in the fluid. For Newtonian fluids like water or something like that, that's totally true. Okay. For something like those suspensions we've mentioned, that's where it could get complicated depending on what am I suspending. If I'm suspending some platelets, and blood flow has platelets, then those platelets actually do have kind of a preferred directions, and they like packing parallel to each other better than orthogonal to each other, right? So there will be some directionality to that. So those could be possible sources of something that is not isotropic. In terms of porous media, same thing. If I'm packing a porous medium that has particulates that are kind of randomly oriented and just put together, I don't necessarily expect that I will have any difference in directions. But if I have plates that have platelets that will orient themselves parallel to each other, then I will have definite differences in terms of how do I flow through each of those directions. So yes, directionality does happen sometimes, but here in general bulk fluid, Newtonian fluid, we don't have it. Okay? So in that sense, I have to have all of these. If there's no preferred direction, then there's no reason for these to be different, right? So they have to be the same. And there are all of these coefficients that are shared for directions ij. So what we actually come down to is that I have basically, since I typically have the same directions for ij, ji, that's because of that symmetricity. So every time I'm describing either ij or ji, I'm going to have this kind of symmetric combination come in. Also mathematically, if you remember, if you have a twice continuously differentiable function, then partial vi, partial j will be the same as partial vj, partial I. So for very smooth mathematical fields, these actually two partial derivatives are the same. So what it really comes down to after some simplification is that I really have two relevant coefficients. Okay? And I will have that tau yj is in general described as minus a times this combination here that combines all of the directions in equal way without saying one is more important than the other. So I have partial derivative of vx with respect to x, partial derivative of vy with respect to y, and partial derivative of vz with respect to z. And that's going to be this cool mathematical operator that we're going to refer to called the divergence. And then I have this symmetric pair here. Okay. So if I actually put this down, for that tau yx where I only have vx component and I don't have vy, and I compare that to that Newton's law for tau yx is equal to minus mu dvx dy. Okay. dvx dx, so if I have vx of y in our first example that we started with, then dvx dx is 0. Right? Vx depends only on y. This is 0. Vy doesn't exist, Vz doesn't exist. So this divergence part is simple and 0. So my tau yx has to be equal to minus b dvy dx, which doesn't exist, and dvx dy. That's the only one that does. And therefore, when I compare the two, I have that b is actually my mu that I've introduced in Newton's law. The second part I'm not going to get into. There's quite a bit of fluid dynamics theory that goes behind this. So basically what it really comes down to is that I'm going to call this b mu, which is the mu that I know, my viscosity coefficient. Okay? And the other coefficient shows up really only for compressible fluids. For incompressible, being incompressible is equivalent with having divergence 0, which however complicated a divergence might be, that's kind of a cool, it's something that gives me an indicator, am I compressible or not? And in more general case, what really it identifies is if you have a source, if you're kind of flowing out of a point, you're going to have a positive divergence. If you're disappearing into a point, and flow could disappear into a point, I could have a sink or source, okay? Then I'm going to have divergence that is negative. And if I'm balanced and I don't just appear or disappear, okay, then I'm incompressible, locally at least at that point, and my divergence is 0. So it's basically a mathematical operator that can look at the vector field and tell me what's happening physically. So my tau yj is minus mu this dvi dj plus dvj di. Now I want to, if I actually want to write this in a tensor notation, so I just want to use an entire tensor. This is basically for each, I have each of the 9 values in my table here, right? They're described, I just replace I and j with the ones that I want. So I can get x, 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 y, x, z, and so forth. But I want to write this actually as a tensor. So what is the tensor that describes dvi dj? mentioned it briefly at the end of the last class, which was yesterday, shouldn't be too terrible. Jacobian, right? So it's my vector, my tensor of partial derivatives, and because I have three possible values of my vx, vy, vz, right, at each point, and I have three possible directions to take my partial derivatives in, I'm going to get a table of 3 by 3 values that describe that. So basically, one of these is basically just, when I look at it, it's basically a value from that tensor, and the other one is that tensor but transposed, right? So what I really have here, so this here is a divergence. That's actually a number. It's just a number times delta ij. I know how to write a matrix for delta ij. That's my identity matrix, right? So if we want to write this down, we're going to get that my tensor tau is minus mu gradient of v. This is a tensor. So when gradient works on a vector field, I get a tensor because I can take partial derivatives in all three directions for three values in this vector. Okay, so that gives me 3 by 3. Then that same Jacobian transpose. This is Jacobian or gradient of a vector. Plus, this is a coefficient. Okay. There's viscosity, and this kappa we call dilatational viscosity. It is not Boltzmann constant. There's two different fields we were looking at, or two different areas of science. And then I have a divergence, which I'm going to pretend like it's a dot product of my gradient operator dot this vector. And why this is useful, just mentally to remember, is that dot products, they take two vectors and produce a scalar, right? So this is acting on a vector, but it's producing a scalar. So divergence gives me just a single number for my vector field at every point. So gradient gives me a tensor for a vector field, and divergence gives me a number. And that's multiplying identity matrix. So when I look at it, now that I understand what all went into it, but I got a way to write it in a shorthand notation, I just hope that you're not going to get scared of this cryptic business here. So if you get panic, okay, just come down and say, okay, all of this is just a shorthand notation for the complexity that happens when I have a vector field and I'm looking at what differences exist in all of the possible directions for this vector field. Yeah? You mind? Though I started at, I'm counting on a 50-minute class and we're on some sort of off clock. Or is my clock off?
5 minutes.
So 5 more minutes. Okay, let me go for 5 more minutes, please. Okay. So now this is it for generalization of Newton's law. And this particular description works for Newtonian fluids. Okay? So for fluids that immediately move when I let them go, and that act like water and gases that are around us that we're typically used to. So they're the ones that are most common in our experience, water being the most common, really, water and air. Right? So now, those other common fluids, like we were mentioning toothpaste, that we should be familiar with 2 to 3 times per day. Okay? Those are non-Newtonian fluids, and we're going to deal with that too, and they're going to have a slightly different description here. Okay. Again, but stress tensor remains stress tensor. I can still describe them with the stress tensor. It's just that stress tensor, I'm going to have to work with my velocity field in a different way to get it. Okay. All right. Now, this is now viscous forces. And it's sort of like a steady state situation where things kind of don't change. There's one more thing that I have to bring in, and that is the matter of Where am I positioning myself with respect to the fluid? So I can observe fluids, and we do, in two different frames. One is flowing with the fluid, okay? And another is actually just sitting in a point and watching the fluid go by. So when I'm watching the fluid go by, so often our measurement instruments are actually stationary. Well, it depends. They could go either way, right? But if they're stationary, and every time, at every point in time, I'm looking at the same location. However, that same location is observing a different packet of fluid. Right? Because the one that I'm just watching right now, next moment, it's gone. And I have new fluid coming in. So some of the momentum is not just relative differences between layers, but it's simply flowing in. If I'm moving with the fluid at the same velocity, I'm observing friction just in that frame, and that we described fully by this shear stress tensor. But if I'm actually thinking about the fact that different physical fluid is moving in to a point, if I'm stationary at a point, then I have to account for that. It's a little difficult to grasp, but I have to account for that. Because I might be looking at physically different fluid. And if I have a multi-phase flow situation, that could be, even the type of fluid could change. The type of my mu could change. Mu for water, mu for oil. Could be a number of orders of magnitude apart, right? You go from 1 centipoise to 100 in no time, right? So I gotta be able to change that and account for the fact that I'm actually moving something in. Okay? So that is so-called convective momentum transfer. So if you actually monitor a packet of fluid, okay, at this moment in time, it has momentum rho v. And if I'm trying to transfer that across three different planes, then the part of it that gets across my, where's my piece of paper? My y-plane, my favorite y-plane, okay? So part of that actually gets moved across this direction is carried by velocity vx. It gets transferred with that rate, vy. So rho v vy is basically transfer of momentum across y-plane. Just this physical carrying things in. So basically, I'm going to have rho v is my momentum, rho v vy is portion of momentum, rho v being the momentum field, carried in y direction at that particular moment. And then I'm going to have a vector for that, because my rho v vy is actually rho vx vy, rho vy vy, and rho vz vy. So this is actually flux of x, momentum in y direction, that is basically carrying it as convection, not because of some friction between the layers. Okay. So this is basically literally moving things this way, as opposed to little molecules bouncing into each other, and those that have different momentum are transferring some of their momentum to the parts where I have less. I'm essentially breaking that apart to two components. Mathematically, I'm looking at it separately. So then I'm going to have this vector describing really just momentum transferred across in y direction. So obviously, if I'm accounting for transferring across my x and my z, I'm going to have no. This was my y, sorry. This was my x and z, right? So all three of them, I'm going to again have 3 by 3 numbers. And I'm going to denote that as simply VB. So when you have two vectors next to each other, it's not a dot product. It's just a tensor that has all of the combinations in correct places. So Vx, 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 Vy, Vx, Vz. Vy Vx, Vy Vy Vz. And again, if you flip x and y, it doesn't matter because it's symmetric. So that is going to be my convective momentum flux tensor. And yes, I have to account for that too. And we arrive at our combined momentum flux tensor that has our molecular component broken into thermodynamic pressure and viscous stresses, plus this convective part that simply flows into that stationary point. Because I'm tied to XYZ, this is done in XYZ coordinate system. So this portion here is my XYZ coordinate system description. Okay. This portion here is a generic tensor notation. And if I translate that to a cylindrical coordinate system, it's still valid. My observations are still valid. If I transfer that to a spherical coordinate system, my observations are still valid. And we know mathematically both my XYZ Cartesian coordinate system and cylindrical coordinate system and spherical coordinate system are all orthogonal coordinate systems, meaning that their coordinates are orthogonal to each other at every point. Now in my cylindrical coordinate system, I'm going to borrow myself a cylinder here. Okay. In my cylindrical coordinate system, my r direction vector might be changing at every point where I'm moving. In x, y, and z, x's are always in the same direction. I just translate them around. Y is same thing, z is same thing. But here actually, it depends. I need to know where my origin is, and my r coordinate vector is changing in the very points as I'm moving around. However, my coordinate direction r, my coordinate direction phi, which is tangential to this surface, and z are always orthogonal to each other at every point. They might be changing, but they're always orthogonal to each other. So they're orthogonal coordinate systems. And actually, same for the sphere. So I actually have matrices that translate one coordinate system to the other. Okay, so it's a mathematical operation of matrix vector multiplication. Okay, that we learned sometime in linear algebra back in the day. And back in the day, we did not understand why the hell do we need it. Okay? But actually, it all comes into focus and transfer phenomena. Because we will have to master specifically cylindrical coordinate system and going back and forth between these directions. Because guess what? Velbor is a cylinder. Perforations are cylinders. Okay? All the engineered systems are mostly cylinders. Are your water pipes in your house or whatever, here in the department, wherever, sewer system is cylinders, okay? So all those systems are cylindrical, so we need to know cylinder well. And here and there, yes, we are actually flowing around particles, such as particles within drilling fluid and so forth. And we have to know how to describe things as spherical coordinate systems. So we can basically describe this in different coordinate systems, but we have it all here in this generalization. So pressure plus shear stress plus convective component. Okay? All right. Think about it until tomorrow morning, and sorry for going. Sleep well. Dream about tensors.
Oh yeah. I have a question from the assignment. Can I ask you now?